Okay, so I wanted to recap the last video because I had to upload it to YouTube instead of Facebook. And I don't think people are engaging. I mean, I don't think it's engaging a lot of people with my content on Facebook anyway, but definitely didn't engage very many people on the YouTube video. So I know how it works with Flat Earth. I mean, I know this subject is not liked by social media. It is what it is. But if we're looking at this video, I'm going to link to the video below. But we're starting out with an empty horizon, and if we zoom in on the horizon, you can see there's absolutely nothing visible. But you'll see if you watch the video that as you zoom in, things become visible because of the camera, right? A camera can take in more light than our eyes can. But if I zoom in there, I can't see anything, but I do you see that thin line above? That thin line above is the lower level of the atmosphere. And we see this a lot. I mean, if you're really paying attention to pictures taken over water, you're going to see a lot of this. And you're also going to see pictures of the water in the distance. Now, this might be the water in the distance, but I believe it's the actual layer that we're looking at. I could be wrong. Either way, it's pro-flat Earth. We're weighing the evidence here. And that definitely, if you can see the water beyond where the visible water is, and that's higher than it should be, you're going to have a real hard time explaining how the surface is refracted into the sky, right? You can't say that's refraction because of the angle. But as we zoom in, we're looking at the boat that's on the horizon. You can clearly see it's entirely visible. The green line represents the last water that we can see. So again, if I'm looking miles through the atmosphere at the boat and the horizon is above the boat, right? Above the front of the boat there where it should be. In order to see that, I've got to look a lot further, right? So I'm looking through a lot more air, and that air is obscuring my view of the water that is in the distance. And as we zoom in even more, you can see that the entire boat definitely visible above the horizon. But you have a mirror line that is dragging the bottom part of the boat into the water as the boat is rising above the surface. So when you watch the video, what you'll notice is for the first about 6 minutes, the entire boat is rising above the surface of the water as the bottom is being pulled down more and more. The top of the boat is converging with that line. So if you imagine a triangle away from you converging to a point, the top of the boat is converging to the center. The bottom of the boat is converging to the center. But because that light is traveling over such a vast distance, if we assume the Earth is flat, which is really the only observation you can make, if you assume the Earth is flat, the light is going to hit the ground over distance because it's refracting down. That boat is taller than me, right? And on the globe, we're going to do downward refraction no matter what, because that's the only way that makes observation make sense. So downward refraction on a flat Earth is going to cause the light from the bottom of the object to hit the ground before it hits my eye and before the light from the top of the object hits the ground. So what we're going to observe as this boat moves away, the first thing I want you to notice is there are 3 dots on the side of the hull. I don't know if those are letters or windows or what in the world that is, but if you look below the bridge, there are 3 letters on the left side there, or 3 windows, whatever it is, and then you have the bridge above that. Now, we're going to be watching from this point on, because what's going to happen is the light from the very bottom of that ship is going to hit the ground or go above my head, right? So if it's going to hit the ground, it's going to make it to where it's not visible, right? But the light above that is hitting my eye, right? The part of the ship that I can see, that light is hitting my eye, and it is also refracting down. So it's coming up on the globe model, it's coming up at an angle to my eye, and it's refracting down and entering my eye at a downward angle, which is going to make that boat look bigger than it is. And that's what we're going to see. We're going to see the part of the boat that is visible keeps the angular size of the top of the ship, because the angular size is determined by what we can actually see of the boat, right? So as it moves away, what is the top of the boat? The mast, right? As it moves away, we're looking at the top of the boat. That is the last light that is going to disappear from our eyes, right? The rest of the boat is going to disappear because the light, as I'm moving away from it, more and more of that light is going to hit the surface over distance. And you can see the top of the bridge and the mast. So we're looking at the top. The top is going to determine the actual angular size of the boat because that light is going to hit the surface last. Here we can see the proportions of the boat. You can see that the bottom third of the boat is the hull and part of the bridge. The middle third of the boat is the bridge itself, and the top third of the boat is the mast. So we can look at that as it moves away. You also have a timestamp down here in the bottom. So we're 2 minutes and 33 seconds into this video. You can see where the mirror line is. That mirror line is going to rise in conjunction with the boat based on the angular size of the boat as we watch it move away. Here we see what the atmosphere is doing to objects in the distance that are further than the boat. And again, this boat, a lot of it is above the horizon, but a lot of it is hitting the ground. And look at how the top of that is being twisted, right, back to the surface. But again, our boat that we're watching, 3 minutes and 59 seconds into it, is continuing to rise above the surface. And again, 6 minutes and 20 seconds into it, if we look at it, now, first of all, what I wanted to point out was those windows on the side. Do you see how they're being pulled all the way down into the water? That the angular size isn't changing, but because I can now only see part of those windows because the bottom part is hitting the ground, it's stretching that all the way down to the surface. But the angular size above the boat, above the water, is remaining the same. Again, the proportions, when we look at the proportions of the boat, they're relatively the same as what they were, but the bottom part of that boat is now being stretched down. Notice how that mast is stretching out more and more. Well, we're going to watch that mast get larger and larger as that boat moves away because we're actually seeing the mast, right? That's actually above the gradient where that angle hasn't hit the ground yet. That is where it is, right? So as that ship is rising above the surface, the mast is remaining where it is while the rest of the boat that is being obscured, not because of curvature, but because of refraction, is being pulled down to the surface. And if you look in this image, barely the bridge is visible, right? Now you don't have the bottom part of the boat being pulled down. Do you see that black spot down at the bottom is gone? That didn't go behind the curvature. It's hitting the ground. The light coming from that is hitting the ground over distance. Now we're too far away to see that light. It's hitting the ground way over there in front of us. Think about it logically. But the angular size of the ship isn't going down behind the curvature of Earth. It's remaining the same. And again, as it moves away, now only the bridge is above the water. The entire hull has been sunken down into the water, but the angular size with the hull and everything where it was above the water remains what it should be. It's converging. The top, the mast is moving away, so it's getting a little bit smaller, converging towards that center. The bottom is rising up, moving towards that center, but the light from the bottom of the ship is hitting the ground, meaning the top of the ship that I can see, all of that light from what I can see is being stretched all the way to the surface because we're seeing it refracted. Look at that huge door, right? That door is as big as the hull was. That is the door to the bridge. Look how big those windows are. Look how big that mast is getting. That bridge is bigger than the size of the hull and the bridge, right? I mean, it's huge. It's gigantic. It's not that big, but it's being stretched down because the light that's hitting the ground, I can't see that. It's hitting the ground in front of me. And here, I just thought that was a cool picture. I mean, look at that boat, clearly above the surface. Our boat is clearly much further away. And as it continues, look at the door now. The door is completely dragging down. And now we're only seeing the very, very top of the boat. Half of the door is now into the surface. But the angular size, look at the angular size compared to the buoy. Look at where the top of it is. The top of it on a flat earth is exactly where it should be. The only thing we're seeing is the light bending through the atmosphere. And as we move forward, now the bridge is completely gone. Only the very, very top of that bridge remains. And it's all being stretched down to the surface. Angular size remaining the same. Now the mast takes up half of the ship. Okay, do you see the line? Do you see the mirror line, how high that mirror line is? That entire top of that boat is being pulled down into the water. And do you see the mast down there at the surface of the water? Do you see how that's being pulled down all the way already and it takes up the entire angular size of the ship? Look at the boats in the distance that are also disappeared into the atmosphere. Now, we're so far away. Do you see how the sky is blocking it? How we're looking so far that not only the sky, but also the wave action. The wave action that's much closer to me is obscuring a large part of the angular size of whatever it is that we're looking at, right? And it's also, you got to think of the light traveling through that layer that's right above the water that's turbulent. That water is clearly very turbulent. And again, we're seeing, because the light is hitting the ground, we're seeing that mast, the only thing that we're going to be able to see being stretched all the way down to the surface. The entire top of that bridge now is disappearing into the atmosphere. The only thing that is where it should be, look at it standing above that boat. The angular size of that ship is still what it is above the horizon based on the mast, and the mast is being pulled down entirely into the water because of refraction, and we end up with this. This is not curvature. The top of the mast is where it should be based on angular size and distance, but the entire mast, the very, very tippy top of it, is being pulled down into the surface because the light is hitting the ground over distance. And as you get further away, the atmosphere is also obscuring what you're seeing. Very simple, very logical, and I don't see how you can look at it any other way.